Welcome to this explainer. I'm absolutely thrilled to guide you through today's topic, because honestly, we're looking at something most of us use every single waking second, yet we rarely stop to truly appreciate it. Today, we're focusing specifically on section 6.1 of our source material. We're going to explore the mind-bending mathematical scale of our auditory system. And I promise you, by the end of our time together today, you're going to look at, or actually scratch that, listen to, the world in a completely different way.
So I want you to take a second and just imagine something for me. Think about the absolute quietest sound you could possibly perceive. Maybe it's a single leaf brushing against a window pane in the dead of night. Or maybe the faint hum of a refrigerator 3 rooms away. Just hold on to that barely there whisper. Okay, now, I want you to contrast that with the loudest, most aggressive sound you can physically tolerate, like a roaring jet engine at takeoff, or standing right in the front row of a heavy metal concert. That vast chasm between those two experiences, the whisper and the roar, well, that's exactly what we're mapping out today.
Okay, let's dive right into this. Before we can really talk about the extremes, we need to set the parameters of our playing field. And in a biological and scientific context, this playing field is called the dynamic range. Simply put, the dynamic range of a system is the range of levels over which that system operates effectively to a certain standard of performance. So, to truly wrap our heads around the dynamic range of human hearing, we've got to find the floor, meaning the absolute lowest level we can process, and the ceiling, the highest level we can handle before the whole system just kind of breaks down.
Section 6.1.1, Absolute Threshold. So let's start at the very bottom. This is our biological floor, the realm of near silence. The absolute threshold is defined as the absolute lowest sound level a listener can perceive when there are absolutely no other competing sounds present. If you've ever had one of those professional hearing tests, this is exactly what the audiologist is looking for. They put you in a soundproof booth, right? And they play these pure tones at very specific frequencies. Then they keep lowering the volume of that tone until you literally can no longer signal that you hear it. That breaking point, that right there is your absolute threshold for that specific frequency. Now, what's really interesting about this slide is the graph we get when we plot those absolute thresholds across different frequencies. I really want to draw your attention specifically to that thick, black line at the very bottom. It's labeled Absolute Threshold, or MAF, which stands for Minimum Audible Field. Do you notice how the line isn't just flat? It actually dips down pretty significantly right in the middle of the graph. On this kind of chart, a lower point means you need less sound pressure, basically less volume to actually hear it. So that pronounced dip, that means our ears are highly sensitive in that specific middle area.
So let's break down exactly what that dip represents. Humans have a total functional hearing range of about 20 Hz at the extreme low end, all the way up to 20 kHz at the high end. But here's the kicker. We don't hear all those frequencies equally. That dip we just saw represents a biological sweet spot for peak sensitivity, right between 1,000 and 6,000 Hz. For sounds outside of that sweet spot, especially near the extreme edges of our hearing range, the absolute threshold is surprisingly high. In fact, you might need 80 decibels or more just to barely detect a sound at the extreme low or high ends of our range. And as the data shows, our hearing thresholds increase incredibly rapidly above 15 kHz, which basically means our sensitivity just drops completely off a cliff. Now you might be wondering, why do we even have this specific sweet spot? Well, it all comes down to some absolutely brilliant biological engineering. You see, our outer and middle ear aren't just simple funnels. They have specific resonances. They physically act as a natural amplifier for sounds specifically falling between that 1,000 and 6,000 Hz mark. Sounds within this mid-frequency range are transmitted through the ear canal and the tiny middle ear bones into the inner ear, the cochlea, with far greater efficiency than sounds outside of this range. We are quite literally shaped to hear these specific frequencies best.
Section 6.1.2, the upper limit. All right, so we've found the floor, we know the quietest sounds we can detect and the frequencies we're best tuned to. Now let's dramatically shift gears and look at the exact opposite end of the spectrum. The main question here is simply, how loud is too loud? Finding the upper limit of human hearing isn't just a matter of signal processing, it's heavily dictated by what our physical bodies can actually endure, because at a certain point, sound stops being just a sensation of hearing and literally becomes a sensation of physical feeling.
Now, tolerance definitely varies from person to person. Some folks with a condition called hyperacusis have a very low tolerance even for moderate sounds. But if we're looking at the general population, the source data gives us some very clear benchmarks. At 110 decibels, sound becomes quite uncomfortable for most people. But when you push that level just a bit higher, above 120 decibels, the experience shifts radically. Most of us will experience something akin to actual physical pain. And it's absolutely crucial to note that exposure to these extremely high sound levels, even for just a really short period of time, risks permanent, irreversible damage to the ear.
120 decibels. That is the magic number that anchors the top end of our dynamic range. And what's really fascinating about this threshold is that while our absolute threshold, the quietest sound we can hear, is highly dependent on the frequency of the sound, this upper limit of pain is almost entirely irrespective of frequency. Whether it's a booming low frequency or a piercing high-pitched squeal, once it hits that 120 decibel mark, it just hurts. Plain and simple.
But physical pain is only one way to define an upper limit. We have to ask another critical question here. What about our functional ability to actually use the auditory system at these extremes? I mean, sure, a sound might be playing at 140 decibels, but can our brains actually distinguish it from a sound playing at 130 decibels? Or does it all just become one giant wall of noise?
This concept is known as intensity discrimination, and the research we have paints a really clear picture. Below 100 decibels, our auditory system is great at distinguishing differences in sound levels. We can easily tell them apart. But as we cross that 100 decibel mark, our ability to detect those differences begins to rapidly deteriorate. By the time we hit 120 decibels, intensity discrimination is still functionally possible, but our system is essentially maxed out. Our processing power hits a wall at the exact same point our physical pain threshold kicks in.
So, the crucial point is this. When we bring the absolute floor of our hearing together with the absolute ceiling of our physical and processing limits, we finally get our definitive answer. The total dynamic range of human hearing, which is the range over which the ear operates effectively, is about 120 decibels in our mid-frequency sweet spot of 1,000 to 6,000 hertz. Now, that range decreases if we go lower or higher in pitch, but 120 decibels is our absolute maximum operational span.
Now, 120 decibels might just sound like a simple number, right? Maybe it just makes you think of the volume dial on a really loud stereo. But decibels are on a logarithmic scale, which means they are incredibly deceptive. Let me put that 120 decibel range into perspective for you. Mathematically, a range of 120 decibels represents an increase in sound pressure by a factor of 1 million. So from the absolute quietest sound you can hear, the pressure pushing against your eardrum has to multiply 1 million times to reach the threshold of pain. It's wild.
And this brilliantly illustrates the true scale of what we're actually dealing with here. Because while the sound pressure increases by a factor of 1 million, sound intensity, which is the actual acoustic power of the sound wave, increases exponentially more. 120 decibel dynamic range equals an increase in intensity by a factor of 1 million million. That is a 1 with 12 zeros behind it. 1 trillion.
I really want you to just sit with that for a moment as we read the exact quote from the source material. The quietest sounds we can hear are about 1 million times less intense than sounds near pain threshold. Let that sink in. Think back to that quietest sound you imagined at the start of this explainer. Now multiply its physical intensity by 1 trillion. That is the sheer, staggering mathematical scale of the sensory instrument sitting inside your head right now.
But this leaves us with an incredibly profound mystery. If our physical ears are hit with a trillion-fold difference in acoustic intensity from the absolute bottom of our range to the top, how on earth does our brain actually translate that massive physical change into the smooth, everyday subjective experience we just casually call loudness? How does the nervous system code a trillion-fold difference without completely overloading? Well, that is the fascinating puzzle of loudness processing, and that is exactly the cliffhanger we're going to leave you on until our next installment. Thanks so much for exploring the dynamic range of hearing with me today.